People tell me all the time that what I do isn't real. They say there's no way you can preserve actual snowflakes. They'd melt, or it's just glue on glass. I understand why they would say it. If I hadn't spent years in the cold watching these fragile things hold their shape, I might not believe it either. On the surface, it sounds impossible that something made of vapor and silence could stay, could last, but it can. And the reason it can is because of science. There's a strange comfort in disbelief. When people say that's fake, what they're really saying is, I would rather believe in the rules I already know. Snow melts, that's a rule, and rules feel safe. But snowflakes themselves are rebels. They form out of dust and pollen miles above the earth, where air is so thin that sunlight passes through without warmth. Water vapor finds a speck, freezes, and begins to build molecule by molecule, always in six-fold symmetry because of how hydrogen bonds align. Every gust of wind changes the pattern. Every shift in humidity redraws the edges. Each one is a map of chaos written in geometry. So when I say I preserve them, I get the disbelief, because how could something that fragile survive touch? It doesn't, not as ice. It survives because we can change it. Chemically, not artistically. The snowflake doesn't disappear, it transforms. The water becomes part of a solid molecular network, turning what was once frozen vapor into clear polymer glass. Long before I ever stood in a snowstorm with a paintbrush, scientists were already asking the same impossible question: can you keep a snowflake? In the early 1940s, atmospheric researcher Vincent J. Schaefer developed Formvar. A polyvinyl acetal film was dissolved in solvent and gently brushed over snow crystals. Schaefer's work changed meteorology. For the first time, scientists could study the exact shapes of ice crystals under stable conditions. His research laid the foundation for cloud seeding experiments and frost studies. Formvar was the world's first true snowflake preservation medium, a scientific success. By the 1950s and 60s, field researchers began experimenting with acrylic and lacquer sprays to stabilize frost feathers and large-scale ice patterns. Those methods worked for macro structures, window frost, ice flowers, but were far too coarse for single snowflakes. Then, in 1979, an Icelandic chemist named Tryggvi Emilsson published a paper describing something radical: ways to stabilize individual snow crystals using a thin liquid adhesive that hardened instantly. He used cyanoacrylate, the active ingredient in superglue. When it touched ice, it reacted with the trace moisture and polymerized, hardening into a solid clear film before the crystal could melt. And that's where the modern story of snowflake preservation begins. Formvar made replicas, Emilsson made transfer. So what actually happens? When resin meets a snowflake, chemistry wakes up. The reaction is called polymerization. Individual monomers, tiny molecular building blocks, link into long repeating chains. Those chains solidify almost instantly, forming a transparent network that locks the snowflake's lattice in place. The result is the same water, same snowflake in a different form. Its geometry, its molecular spacing, preserved exactly as it existed in that. The ice itself changes state, but the pattern, the architecture of the storm remains. No evaporation ever occurs. Think of it like amber isn't the tree sap anymore, but it holds every detail of the insect trapped inside. Preserved snowflakes are the amber of winter. Most people who try this will fail their first time. I did. My entire first winter was failure after failure. I melted snowflakes, shattered slides, lost entire trays to the wind, and sometimes the resin was too warm, sometimes the air too dry. There's 1,000 ways for a snowflake to vanish, and only one perfect way for it to stay. And yes, it is something people can try at home. It takes steady hands, freezing air, and a respect for timing. Your slides must be chilled for at least half an hour. Your resin, whether cyanoacrylate or Formvar, must be equally cold. Even the warmth of your breath can destroy everything. This is why snowflake preservation isn't a quick craft. It's a collaboration between chemistry and patience. The snowflake does most of the work. You just have to learn to listen. Every snowflake begins as a single grain of dust. Water vapor condenses around it and freezes, building outward in a fractal system. The colder the air, the sharper the arms. The higher the humidity, the more elaborate the branches. At 20 degrees Fahrenheit, -6 Celsius, you'll often see the large classic six-pointed stellar dendrites. At -10 degrees Fahrenheit, -23 degrees Celsius, the shapes shrink into needles and plates. Each one is an archive of the air it fell through, a weather record small enough to hold on your fingertips. But they're mostly empty space. They break with a sigh. The heat of your hand, the moisture of your breath, even the static from your sleeve is enough to destroy their form. So to preserve them, you have to meet them on their own terms. In the cold, people often ask, well, where does the water go? And the answer is, it doesn't go anywhere. In cyanoacrylate preservation, some of the water becomes part of the polymer network. The rest of the snowflake is actually air. In the Formvar method, the ice sublimates slowly beneath the hardening film, leaving a microscopic cavity. Either way, the snowflake's pattern survives. So when you look at a preserved snowflake, you're seeing the exact geometry of the ice it once was, a new stabilized material that will likely last for hundreds of years. The night my first snowflake finally held, the world was silent, the kind of silence that only comes after a heavy storm. I lifted a crystal onto a chilled slide, touched it with the tiniest drop of resin. I had failed so many times before that I didn't dare hope. But when the surface hardened and the snowflake didn't vanish, I lifted it and immediately stocked it into the freezer to cure. 2 weeks later, it was still there. Perfectly six-pointed, clear as glass, not ice anymore. Something between matter and memory. That was the night I realized this wasn't just science. It was devotion to patience, to wonder, to proof that even fragile things can endure. Most of my work happens in silence. I know lots of people want to hear that I listen to music and do all these things, but the world outside is asleep and I am in my studio with trays and slides and the air is so cold it hums. There's no glamour to it, just stillness and time. And sometimes after hours of work, nothing survives. And that's the beauty of it. Failure becomes a teacher and not a punishment. Because when you do catch one, when you hold a snowflake in your hand and it stays, you feel the entire sky condensed into a singleness. Every preserved snowflake I hold is proof that transformation isn't lost. It's nature's most elegant magic trick. The ice becomes something new, and maybe that's what we're all doing, learning how to change without vanishing. People think of snowflakes as fragile art, but the chemistry that saves them is tougher than steel. If the snowflake itself is the painting, then chemistry is the frame that keeps it from fading. Long before art ever met snow, scientists were the first to try to keep one alive. In the 1940s, Vincent J. Schaefer, the same Schaefer who later helped pioneer cloud seeding, worked at General Electric Research Laboratory. He was studying how clouds formed and why some release snow while others don't. To study snow crystals, he needed them to stay still. He discovered a polymer called Formvar, a polyvinyl acetal film that could be dissolved in solvent and brushed gently across the slide, holding a snow crystal. As the solvent evaporated in the freezing air, it left behind a clear film that captured the exact ridges, branches, and plate structures of the original crystal. For the first time, scientists could study snowflakes long after the storm was gone. No longer were we sketching and hoping. Schaefer's method, it wasn't art, it was research, and it changed meteorology forever. You can check this out through Caltech Snow Crystal Archives, Schaefer's 1940s GE research papers. Acrylic and lacquer. In the 1950s and 60s, field researchers were spraying entire branches, windows, and frost feathers with clear lacquers and acrylic films to preserve patterns for study. It worked beautifully on large ice forms, but not on individual snowflakes. The solvents evaporated too slowly, and heat from the aerosol melted the crystals instantly. Still, these experiments helped scientists understand that preserving a snowflake was less about freezing it and more about stabilizing its geometry before melting could begin. Then came 1979. An Icelandic chemist named Tryggvi Emilsson was working in the kind of cold that never lets you forget where you are. He published a short paper outlining a radical idea, a liquid adhesive that could turn solid the moment it touched ice. That liquid was cyanoacrylate, the active ingredient in superglue. It reacts with moisture in the air to form long molecular chains almost instantly, a process called polymerization. The reaction is exothermic, but so rapid that when performed in sub-freezing temperatures, the ice remains intact long enough to be encased. When it hardens, cyanoacrylate becomes a clear thermoplastic, chemically related to acrylic glass. So technically plastic, but it's inert. Stable, museum-grade plastic used in airplane windows and medical adhesives. Once cured, it does not release toxins or break down into microplastics. Source: the U.S. National Library of Medicine, cyanoacrylate, biocompatibility review, Caltech, snow crystal preservation methods. Polymerization and transformation. When resin meets ice, the water does not vanish. It joins. It causes the reaction. Moisture acts as the trigger for polymerization. It starts the chain reaction that turns monomers into long-linked molecules. In that moment, you have a living bridge between states. Ice becoming solid, acrylate, crystal turning to glass. The geometry remains exactly as it was in the clouds. The snowflake is still there, just chemically altered, structurally preserved. Formvar works by encasing the ice and then letting the frozen water sublimate away. Cyanoacrylate locks in before it ever has the chance to melt. Both methods preserve, they just speak different dialects of chemistry. People think that it's their resin that is doing them wrong and causing them to fail, but usually it's the weather. Humidity, wind, vibration, temperature fluctuations by even 1 degree can undo hours of work. There are hundreds of reasons a snowflake won't preserve. Surface tension too high on the slide, resin too warm, air too dry, crystals falling far too wet, hands not steady enough. It's just proof you're learning how nature behaves when you try to hold it. Let's talk about plastic. The word itself sets people off, but not all plastics are equal. The polymers used in snowflake preservation, polyvinyl acetal, cyanoacrylate, and PMMA acrylic, are non-leaching, inert thermoplastics. They do not pollute water systems, and they don't degrade like disposable bags. They are used in microscope slides, medical implants, art, conservation, and optical lenses. They're stable because they're meant to preserve and not disappear. So when someone asks about environmental impact, I tell them this: I capture snowflakes using less material than it takes to print a single shipping label. Science is often portrayed as cold and mechanical, but to me, it's a love story. Every reaction is a conversation between what wants to stay and what has to change. Emilsson's method was born in the same spirit as Schaefer's. Curiosity, reverence. They weren't trying to defy nature, they were trying to understand it long enough to remember it. That's what I do too. I'm not saving snowflakes from melting, I'm helping them transform into something new, something that can be shared, studied, and cherished. Snowflakes are a reminder that beauty and structure can exist in the same breath, and that sometimes holding on to wonder requires a little bit of chemistry. Every capture begins long before the storm. You learn to read the air, the pressure, the way the clouds flatten over the mountains. You start to notice how the wind smells colder before it ever feels that way on your skin. The perfect snowflake forms in calm, steady air around 20 degrees Fahrenheit, the sweet spot, where geometry truly flourishes. Too warm and the crystal merges into slush, and too cold and the vapor freezes and forms little columns and tiny plates. At 5 degrees Fahrenheit, snowflakes are thin and sharp. At 20, they bloom into 6-armed dendrites, the kind that people imagine when you draw a snowflake. Every pattern is a signature of the weather that made it. I capture snowflakes inside a covered garage I've converted into a freezing studio. It stays just as cold as the air outside, no heaters, no warm lights, just quiet, and for me, it's the only way to make this work. The moment you bring a snowflake into warm air, even by a few degrees, it's gone. Everything is chilled, every surface, Trays, slides, brushes, resin, all my tools are stored in the freezer. I've worked this way for years, most often under a small light or moonlight so as not to destroy the crystals. Chasing that brief stillness where science and silence truly meets. It's not glamorous, it's slow and often uncomfortable, but it's the only way to truly see what the sky is capable. I use a fine tip brush to lift snowflakes from where they have fallen and to set them onto chilled glass slides. Sometimes they break before they even land. Sometimes they get a little jostled in the transfer, and sometimes it just vanishes in the air. And the right one stays though, you know. Every branch is a record of the storm above. Polymerization starts instantly. The molecules link, hardening into a clear thermoplastics. The water becomes part of that reaction. It doesn't vanish, it transforms. It's no longer ice, but it's still the same snowflake. The structure remains exactly as it formed in the clouds. So here's what I've learned. The snowflake teaches patience. The melt teaches grace, and both teach gratitude. We are not here to stop time. We are here to notice it, to love it while it lasts, and to leave something behind that helps someone else do the same. Because in the end, it's not about the snowflake at all. It's about the moment it made you look up.